Our presenter today is Ron Martino. Ron holds a Bachelor of Science in Chemistry and has worked in the environmental laboratory field for over 30 years. He has performed a variety of environmental analysis, served as a technical director as well as a lab director before moving to his current role. Now, Ron is the regional account manager at the ALS laboratory in Houston, Texas. Ron, thank you for taking your time today to deliver this presentation. I will go ahead and turn it over to you.
Thanks, Kelly. Good morning, everyone, or good afternoon, depending on where you are in the country. And today, we wanted to put a little presentation together on some of the updates that have been happening with PFAS. I know PFAS has been an emerging contaminant for a few years now, and there's been methodologies out there, analysis out there, regulations and things like that. But it is one of those analytical techniques or sampling techniques that is changing rapidly. And there's always updating, regulations and certifications and methodologies. And we just wanted to put a little presentation together on some of those updates. Now, some of these things that I'm going to talk about can pretty much be a webinar into themselves. And I'm just going to touch them briefly, do a little explanation. And of course, if you need any additional information, we're always available for you offline. So one of the first things, just our agenda. So we're going to do a brief introduction, which is what I'm going to do now. We're going to talk a little bit about brief chemistry. Don't worry, we're not going to have a chemistry test at the end of the presentation. Little toxicological concerns, and then we'll get into the latest regulations, both on the state and federal level. We'll talk about some of the analytical techniques that the laboratories are implementing, some of their new methods that have come about. And also certifications. We're going to talk a little bit about some forensics, where the top assay and the total organic fluorine or total organofluorine analysis. And then some of the market challenges that we're starting to see. And then, of course, you're probably seeing them as well. I won't go too much in detail in there, but just some of the things that we're noticing. So just a brief introduction to PFAS. So, what are PFAS? Well, essentially, they're man-made surfactants, and that is their purpose. They are not an end product that you could buy off a shelf. They are a product that industry uses to make other products. They are both hydrophilic and hydrophobic, which is the definition of a surfactant. So they like hydrocarbons and they like water, and they are very valuable for the production of a multitude of products. Some of those products are everyday products that we use and are unaware that PFAS is in them. They're used in paper products such as sandwich wrappers, burger wrappers, fries, cups, things of that nature. They're used in nonstick cookware, Teflon being the number one that comes to mind. Water repellent clothing. Scotch Guard has PFAS or did have PFAS in it at one time. Stain resistant fabrics and carpets. Some cosmetics, and so basically any product that can resist grease, water, or oil. And of course, where we're most familiar with PFAS is in aqueous film forming foam, or as we know as AFFF in the firefighting foams. So the chemistry is, you'll hear PFAS compounds, everyone just says PFAS, and it's actually a class of chemicals. It's not one individual chemical. PFAS stands for per or poly. Now, the definition of a perfluorinated is all the carbons in the tail are substituted with a fluorine atom. So all carbons have the carbon fluorine atom in the tail. So the first example is a perfluoroalkane sulfonic acid, where the tail end right here, if you can see my pointer, where N is the number of carbons, but you see that carbon is completely bonded with fluorine, except for where the last carbon binds with the, or is bound to the head. In this case, the head is a sulfonic acid. So this is a perfluoroalkane sulfonic acid. Second example is the same thing as far as a per, where all the carbons in the tail are bonded with fluorine, and then this one at the head is bonded with carboxylic acid. So the sulfoxonic acid and the carboxylic acid, they're the ones that are the hydrophilic, or they like being in water. The tails, they are hydrophilic. They don't like being in water, but they like being with hydrocarbons, which enables this compound to pull organic materials into an aqueous medium. And then the last example is an example of a precursor. It's a short chain precursor, but it is considered a poly. And that means many, which means not all the carbons are substituted with fluorine. So in this example, you see where the CN has all substituted with fluorines, but then you have a couple of carbons that are substituted with hydrogens before you get over to the head. So the tail is not completely substituted with fluorines. It is just has many fluorine substitution, otherwise the definition of poly. Okay, so some of the toxicological concerns with PFAS compounds is really the big one, the toxicology, but one of the problems with PFAS, it is a class of compounds that are extremely stable in the environment, hence why they're used in industry. They do not break down under natural degradation. They are actually considered a forever chemical. Now, studies are being done to try to do bioremediation and things of that nature to get these compounds to break down. But the carbon-fluorine covalent bond is the strongest covalent bond that's out there. So a lot of these bacteria or critters that normally would chomp on hydrocarbons, they can't produce enough energy to break that carbon-fluorine bond. So those chemicals stay out there for a long period of time, hence the forever chemical classification. PFAS, since they're both hydrophilic and hydrophobic, they actually bind to the proteins that are found mainly in the blood of us, humans and animals. They do not store in fats like PCBs or pesticides or metals. They actually are bound to the proteins in your blood. And you do have an accumulation possibility in the liver and kidneys. If you think about the liver and kidneys are the fuel and oil filter of the body. So they can filter out these PFAS compounds out of the blood, but then they have accumulation there. The uptake of PFAS compounds is through direct exposure, whether you're drinking water that has been contaminated with PFAS, firefighting foam. A lot of firefighters, they'll inhale those foam particles through skin, and then also through bioaccumulation. So animals that drink water that is contaminated, and then we consume those animals from farm activities also can be ingested, and then of course you get bioaccumulation through that rate. Some of the adverse effects: low infant birth rates, fertility issues, immune deficiencies where you have suppression of the immune system. There has been some clustering of cancers, especially where there's PFOA, and then also high cholesterol. Now, the toxicology is still being studied. It's not set in stone. It's still out there. Some of the stuff is basically from clusters where they've seen a lot of PFAS contamination. They also see these types of problems in humans. The one thing that has noticed is PFAS does not have an acute toxicity, at least not yet. Most of the problems that people start having is due to a chronic influx of PFAS where it just basically starts accumulating in your body, and then you start having these type of issues. Since it's bound to the blood system, men tend to retain the PFAS in greater concentrations than women, but these will always stay in your blood. All right, so we'll start getting into the regulations. So the regulations really are relatively new. We're in 2020. And so what started happening under UCMR 3, they noticed some PFAS compounds in municipalities and came out with advisory limits or health advisory limits for two of them, PFOA and PFAS. And the health advisory limit was set at 70 nanograms per liter or 70 parts per trillion. So there was a health advisory limit out there, but there was no regulatory. So this health advisory limit is non-regulatory and non-enforceable. So it really left a lot of states and of course the federal EPA without any enforcement or accountability if they did find and track back where the PFAS was coming from. So you started having states step up to the plate and come up with regulatory type laws that are out there that allows them to then do what they need to do to have the cleanup. So as it stands right now, only 16 states have promulgated drinking water standards for PFOA and PFAS, and there are some others as well, and we'll get into those. So those states are basically colored right here. So anything that's gray, those are the states with no regulatory PFAS in drinking water at all. The red states, or red state, I should say, has adopted the standard above the health advisory limit. The blue states are at the health advisory limits, and then the orange states have adopted standards below the health advisory limits. So when you're working in a PFAS project, or you have to understand what state you're in. You'll hear me say that several times. So if you're in Louisiana, there is no state regulations for PFAS. So when you're doing something, you really have to figure out what your goal is or what your objectives are for that project. Where if you're in New York or New Jersey, they are regulated and they do have the regulatory body there that you can refer to. So since there's no federal guidelines at this point, you have to be aware of what state you're in. And some states have washed their hands of PFAS. They basically, I've talked to a few regulators that have looked at me and said, don't talk about it. We don't want to open that can of worms. Where other states are very aggressive when it comes to PFAS analysis and detection and cleanup. And so being in those states, you really need to pay attention of where you are and what those state regulations are. So I put this table in here. We're not going to go over this too quickly. There's a lot of information here. Kelly is going to print out this in PDF, so this information will be in the PDF that gets sent out to you. But as you can see, there are a number of states that go as low as 10 parts per trillion for PFOA and PFAS. 11, 12, 13. There's multiple, such as California, where you have 13 parts per trillion for PFOS and 14 parts per trillion for PFOA. Some of the states, such as Massachusetts, where if you look at the Massachusetts, they have 5 PFAS substances and it's a combined amount. So they're at 70 parts per trillion, but it's a combination. So if you find one of these 5 at 70 parts per trillion, you're over the regulatory limit. Or if you have these 5 detects that have a summation of greater than 70 parts per trillion, you're over the regulatory limit. And we'll just move forward through this table. And so North Carolina, which is above the regulatory limit, but they're looking more for Gen X. You may be familiar with the Comores and the Wilmington, North Carolina area. They have a big problem with Gen X, so they're really just doing the Gen X for regulations at this point. And then there are the states there listed that have no regulation whatsoever. So the other thing we need to talk about, or I wanted to talk about, is certifications. A lot of states have come out and they have regulatory guidance now, but those states, we also have to look at certifications. So if you're going out into the field and let's say Florida, you will notice that Florida, if I go back a couple of slides, is one of the states that has no regulation whatsoever, but they do have certification under NELAP. So some of the states out there have state certifications. Some of the states out there have NELAP certifications. Some of the states have certifications with no regulations. Some have regulations but no certifications. So you can see how this can get pretty confusing to you if you're going out into Alaska and you want to do some PFAS sampling for analysis. Well, you're going to need to find a laboratory that actually has the Alaska state certification. And you need to find the laboratory that has those specific certifications for Alaska. So they'll accept for soils and waters the 537 modified as long as you satisfy the QSM 5.3. But for drinking waters and non-potable waters, they will accept the 537.1 method, which is the drinking water method, but also the 537 modified as long as you're satisfying the QSM. But right below it in Arizona, even for the soils, the non-potable waters, they're only going to accept the 537.1, which is a drinking water method. But for drinking waters, they'll accept the new method, 533, 537, which is the revised method, and again, the 537.1. So when you're going out into the field, you want to ensure that the laboratory you're choosing has the correct certification if a certification is necessary, and what state you're in, so you make sure you satisfy the regulatory agency's guidelines. Okay, so on the federal side, there are no true federal regulations at this point. They're still doing some studying. So what they're trying to achieve is what I have listed in the next couple of slides. So for federal regulations in drinking water, they want to start regulating PFOA and PFAS. And they did validate, here I have validation of new method 533, but that method, it actually has been validated and promulgated, I think in January or February of 2020. And 533 focuses on the short chain PFAS compounds. They want to also start working with the cleanup, so they issued an interim recommendations for addressing groundwater contamination with PFOA and PFAS. I have PFOA twice, so I apologize for that. And also guidance for RCRA and CERCLA. They want to follow through on regulatory development for listing certain PFAS compounds as hazardous substances under CERCLA. For monitoring, they will provide nationwide drinking water monitoring for PFAS under the next UCMR cycle, which should be UCMR 5, which should be coming out pretty soon. And then for toxics, they added 172 PFAS compounds to the toxic release inventory. And they also came across and did a certain PFAS chemicals and surface coatings cannot be manufactured or imported into the United States without notification and review under TSCA. The feds are also working on some surface water where they want to develop national clean water for human health and aquatic life criteria for PFAS. Examining available information about PFAS released into surface water by industrial sources and see if additional study is needed. They're also looking into biosolids, developing risk assessments for PFOA and PFAS to understand potential risk or potential health impacts, and continue with some research to guide them through compile, assess human and ecological toxicity for PFAS and also other PFAS type compounds, apply toxicological testing and study the toxicology of the larger universe of PFAS, developing exposure models, and then of course assess any review treatment, cleanup, and disposal technologies. So the feds right now are really in kind of a research mode to come up with the appropriate regulations. We've been told the regulations were coming out in 2019, 2020, so I don't really have, or I don't know of a time frame these will be coming out, but this is what the federal government is working on at this time. Okay, so some of the methods that are out there for analysis that laboratories are performing at this point. Of course, the first one that came out was EPA 537.1. That is the analytical technique that was derived for the UCMR 3, which came out in 2010, if I remember correctly. Since that time, 537.1 has been revised. And so you have a revision 1.1. And the main revision, it went from 14 compounds to 18 compounds, including some of the replacement compounds for PFAS, such as Genex and Adana. The latest one that come out, 537.1 is drinking water only. The latest method that has come out is EPA 533. So you'll start seeing laboratories offer that method as well. A lot of laboratories have brought it online, as we have here at ALS. Some laboratories are still working on it. This is not a replacement for 537.1 revision 1. This actually is designed to complement 537.1 revision 1. but there are some method differences. So when you're out into the field and you've looked at the regulations and you've looked at the certifications for each of the states that you're working in, you also have to understand which method you're going to use. 537 modified, which we're probably familiar with, that was a modification of the original 537.1 method, mainly to capture other types of matrices. So of course, anytime a method is modified, labs can modify those methods in any way they can. So the DoD came out with a table in the QSM 5.1 table called B15. This did not say what the method had to do, but it did say what the method had to satisfy. So there's criteria in table B15 that the analysis has to satisfy. And what that did is it really made the modifications of the methods between the laboratories get a lot more consistent to meet those demands from the DoD. Other methods out there, you have the standard methods, D7979, which is direct injection methodology for drinking water. ASTM method D7968, which is more of the solid phase for soils and sludges. And then, of course, the federal government SW846 methods, 8327, which models itself after the D7979 as a direct injection, and the 8328, which models itself more kind of after the 537 modified with solid phase. And then you also have the more forensic type analysis called total oxidational precursors or oxidizable precursors. You might hear it called as the TOP assay. So this next table that I have coming up, there it is, just kind of a rundown of the similarities and differences of the methods as they pertain. And like I said, ALS has done a presentation on each of the individual methods and how they differ from the method next to it. So if you want to get that information, just let us know and we'll definitely provide that to you. But here's just a quick and dirty table of some of the things that you have to be aware of when you look at these methods. So 537.1 revised, number of compounds 18, matrix drinking water only, report limits. It does not perform isotope dilution and does not satisfy the QSM 5.1 stated in the DoD QSM 5.1 table B13. As I said, EPA 533 is not a replacement for 537.1. It actually is to complement and is designed for the short chain PFAS compounds and has 25 compounds. If you look at the list of EPA 533 and the list of 537.1, they're much higher. In the methods that use solid phase extraction, there's a concentration step, which allows a laboratory to get to a much lower concentration in part per trillion. Where in direct injection, basically it's a dilute and shoot. You take a volume of water, you add a volume of solvent with your surrogates and internal standards, and you load it on the filter it and then load it on the instrument. Now, we've done a project here at ALS where we used both 537 modified and 8327 on the same samples. And the results were very comparable until you got down to the reporting limit, where when you were up into the 30s and 40s and hundreds of parts per trillion, the results were very comparable. But once you got down around 4, 5, 3, and even below 2, obviously the method 8327 became non-detects. So again, be aware of what methodologies you need and what your reporting limits are to ensure that you meet the proper reporting limits. And then you have the two ASTM methods, D7979, which is very familiar to 8327, which is also a direct injection method. ASTM D7968, which was designed for soils and sludges under ASTM, which is a solid phase. And then a new method that's coming out. I don't think it's promulgated, but I know several laboratories are starting to bring it online. is the SW846 method 8328. But if you go back to that original table of certifications, you will notice that very few states are certifying for the SW846 method. I think West Virginia is probably the only one that I can recognize right here for soils. They have the 8327 and the ASTM method D7968. Everyone else is sticking with the 537 or modifications of 537, which a few of them, let's see, I think a few of them may be bringing 533 online. Let's see, where were we? Okay, so now we start getting into kind of more of a forensic type PFAS analysis. There have been studies, and I won't go into much of the details, but when it comes to PFAS, when you're looking at these methodologies, they have a number of compounds that they're looking for. But there have been studies out there that they think there are over thousands of PFAS compounds, both full PFAS and precursors. And so if a laboratory can only analyze, let's say, 30 to 35 compounds, and there's supposed to be 1,000 of them or more, thousands of them out there, how do we account for that undetectable or hidden mass, or sometimes you'll be called as dark matter? So the top total oxidative precursor, or top assay, was designed, and what that basically does is it oxidizes the precursors in your sample using both persulfate, sodium hydroxide, and some heat, and forces those precursors or reacts with those precursors for them to become the PFAS compounds that we do analyze for. So the theory behind this is you take your sample and you analyze it for your PFAS compounds. Then you take more of the same sample, you go through this oxidation process, forcing these precursors over to become PFAS compounds. You analyze them again, and if you get a higher concentration after the top assay, then you know in your sample you have some dark matter or hidden mass. The problem is you don't know how much, because the oxidation process is not 100%, and it only oxidizes the PFAS compounds that can be oxidized. So even though you're going to compare the sample analysis prior to top and post top, it's not going to give you the entire answer. It's just going to let you know that there is some hidden mass and some dark matter. However, it will identify some PFAS compounds that the precursors oxidized into. So I just wanted to put these graphs, these simple little graphs up here. So what we have here on the left is 3 firefighting foams, or four firefighting foams. On the left is just the analysis of the firefighting foam, and you'll notice down below AFFF 1, 2, and 4 have very low concentrations if you consider part per million in PFAS low concentrations. But AFFF number 3 is pretty high, about 13,000 ppm in PFAS compounds. Well, this sample then went through the top assay and reanalyzed for PFAS, and you can see now on the right side that there were plenty of precursors in that AFFF that caused the concentration for every foam to be detected for PFAS. So you have 1, 2, and 4, which barely had any in there, and then it went as high as almost 5,000 ppm. So those precursors were oxidized, and of course AFFF went from about, or AFFF 3 went from about 13,000 up to over 18,000 ppm. So this indicated that when the initial analysis was performed, they did the PFAS and they got results, but there were a lot of hidden mass, a lot of precursors in that AFFF that were not accounted for during the initial analysis. So be aware of that when you're doing your analysis, or when you're doing your sampling, if you're looking for the hidden mass or the dark matter. So even though there's top out there that can get you additional PFAS information, it does have its limitations. So when you're doing a PFAS analysis, 533, 537 modified, whatever method you decide to choose, you're looking at maybe 20 to 50 compounds, depending on the laboratory you've chosen in their compound list. Okay, that's a good start, but there's supposed to be 3, 4, maybe 5,000 PFAS compounds in existence. So you can go to top and get additional information, but there's limitations to the top assay as well. It's not fully quantitative, and what I mean by that is the only compounds you're going to analyze for are the ones that can be oxidized. So if there's dark matter that cannot be oxidized, you're not going to know about it. It is highly sample variable, which means there's a sample matrix effect that will maybe reduce the ability to oxidize those samples. So it doesn't capture all the dark matter. It helps you, but it doesn't capture all of it. So now in development, there's total organofluorine analysis, or you may hear it as TOF. And what this is, basically, in a simple layman's term, is you take the water sample and you absorb all the PFAS compounds and the precursors on some sort of activated carbon or sorbent. And then you combust that material to release the fluorine. So now you just have fluorine in your sample. And then you analyze the total fluorine by ion chromatography. It's a very simple analysis. It really doesn't need special costly instrumentation. It's only applied for aqueous matrices and blood samples. That's an aqueous matrix as well. So you can't really do soils and other type of matrices. You have to be aware that you have to remove the inorganic fluorine and report it as organic fluorine, and it can be developed on a wide commercial scale. The downside to this is you're not identifying what PFAS compounds you're analyzing or what you're looking for. You just know by the total amount of fluorine, you can back calculate how much fluorine you've gotten, then you can back calculate into what PFAS compounds or concentration of PFAS compounds. But you cannot identify where those PFAS compounds came from. So right now, this is pretty high priority for the EPA, and they're trying to develop a draft method and have it come out in 2020. So between the top assay and the TOF, this may be something that we're going to be looking into in the future to help understand all of the PFAS. It may be a combination of doing the 533 method, the top assay, and the TOF to get a full picture. Or it may just drop down into doing, well, if we have X amount of fluorine, then we know we have X amount of contamination in PFAS compounds. So there's also been talk lately in PFAS in air, or in stack gas to be more precise. A lot of source of air emissions that people are starting to look at. A lot of these PFAS compounds, because of their stability, they go to hazardous waste incinerators and of course get burned, but how do we know that all the PFAS compounds are actually being incinerated? So they're starting to look at, do we have to have PFAS in air under hazardous waste incinerators, sewage and sludge incinerators, thermal oxidizers, thermal desorbers, and chemical plants that have process vents that maybe use PFAS on site. So this is a new source. This could be pretty much a topic all into itself. I'm going to be honest with you, I'm not 100% up on this subject, so I just wanted to put some facts out there that it is something that is being looked at. So under the Defense Authorization Act of 2020, all incinerators must be conducted with the Clean Air Act and permitted facility for waste regulator under the Solid Waste Disposal Act. So they're going to start implementing that for PFAS as well. The total toxic release inventory that tracks certain toxic chemicals, PFAS is going to be part of that as well. And there are some laboratories that are developing analytical methods to do PFAS analysis in air or stacked gas. And like I said, this is currently under development. It's not widespread at this point, but it is definitely being discussed, and you might start seeing some webinars on this as well. So the last slide I have is just some of the things that are challenges. I call them market challenges. I don't know if you really want to call it market challenges, but things that we need to be aware of in the laboratory, and I think some of our clients need to be aware of as well. The lack of federal guidelines leaves a lot of interpretation of what needs to be done. So we really have to focus on what the states are doing. So of course the state certifications are not consistent and the state requirements are not consistent. So when you're working in certain states, you have to understand each state might have their own requirements for certifications and of course their regulatory. Of course, with laboratories, as with anything else, everyone's looking for lower limits. So labs are trying to figure out ways to get down to lower limits even more. Methods are constantly changing or bringing online. We've almost every project we get, there's always an addition of analytes. We have 35, someone wants to add 2, now we have 37, then someone wants to add 3 more, and so on and so forth. So the analyte lists are constantly changing. The methods are being updated, almost seems like monthly or bi-monthly. Certifications are changing, and of course the number of matrices. Started out as drinking water, then can we do soils and groundwaters, bloods, biotas, biosolids, things of that nature. And now we're talking about doing PFAS compounds in air. So I guess the crux of it is things are always changing and they're changing relatively quickly. And with that, I'll end my presentation. I apologize if I went through it very fast, but we are going to open it up for questions. So if you have any questions, we'll be glad to field them at this time.
Yes, thank you, Ron. We will go ahead and open it up for questions at this time. Please write out your question in the chat section located again at the bottom right. We already had one question come in during the presentation, but we will give everyone a few moments to get their thoughts. The first question came in from Karen. She asks, do you have any information for Canada regulations?
At this time, I do not, but we definitely can track something down for you. We do have laboratories in Canada, and we can see what their regulations are. If you want to send, my email's right there. If you want to send me a quick email, and I will definitely get with our Canadian counterparts and see if there's anything that's up there.
Looks like we're still having some people write in their questions, so we'll just go ahead and give it a few more moments. I do want all the participants to know that this webinar presentation has been recorded, and all the participants on this webinar will receive a follow-up email once the recording is available to view. We also post our webinars on our ALS Global website and our ALS YouTube channel. I encourage you to find a wide range of video resources and past Webinar Wednesday presentations available there as well. We had a question come in from Dwayne. He asks, any idea regarding the timeline for federal guidelines being adopted?
That's a tough one because the feds have been saying they're adopting these guidelines since 2018, and it just seems like it gets postponed over and over again. So right now, I think one of the slides I had in here, they're trying to get some stuff done in 2020. But with COVID coming around and priorities being changed, and they're still doing a lot of studies. At this point, I'm not anticipating any federal guidelines to be promulgated. I think there's a lot of studies that they're still doing. They're just trying to get all the information they can before they make anything a permanent guideline. So I'm sorry, I just don't see anything like on Tuesday we'll have this for you. It's just not out there yet.
We had another question from Todd. He asks, with the lack of federal guidelines, how do you handle federal and state discrepancies? And what do you recommend?
Most of the federal projects that we're receiving in the laboratory are going through the DoD. Very few, well, that's not true. There is a couple of projects. So a lot of, I'll stay with my original statement. A lot of the projects that we're seeing that are going through the laboratories are going through the DoD, and they're very stringent on the QSM 5.1. Well, it's been updated to 5.3, but that table B15. As long as your laboratory that you're using is DoD certified, possibly state certified, and follows DoD QSM 5.1 table B13, you're going to be okay. As far as we have done a project here in Houston where we worked with the federal EPA and the Texas Commission of Environmental Quality, or the TCEQ. And in those respects, the federal EPA at a Region 5 made us run the samples by ASTM D7979, and the TCEQ made us run the samples by 537 modified. So the consultant at that point, I won't mention their name, they actually had to run 2 different programs at the same time, one for the federal EPA and one for the TCEQ. And that's the example I used where the results were very comparable until you got down into the lower concentrations because the methodologies were different. A lot of times when we work with clients that are working with both the feds and the states, there's a lot of upfront discussions that come up with the game plan that then is put into place. So that's what I would recommend, and that's what I've seen, is there's conversations before people go out into the field and everyone agrees to what's going to happen and then move forward. But as it stands right now, if you're in New Jersey is going to force you to follow New Jersey regulations as opposed to what the federal government's going to want you to do.
We had another question come from Andrew. He says, can you speak about required sampling techniques and bottleware requirements?
Yeah, you can actually have you can have pretty much a presentation on that. So when it comes to sampling requirements, those, I'm not a sampler. I've never sampled before, so I'm just doing this from kind of like an informational purpose. Because PFAS compounds are literally used in almost everything you touch, when you go out into the field, you have to be very aware of that. And it's not because you don't want to get exposed to the PFAS compounds, is you don't want to contaminate your samples. So there's certain things you must be aware of. Number one, do not use anything that has PFAS in it. We're talking bug repellents, sunscreens, makeups, lotions, soaps, detergents for your clothing, new clothing. Do not use anything that has Gore-Tex because that has Teflon in it. You do not want to use Scotch Guard. You do not want to use anything plastic. Clipboards. You have those particulate board clipboards that have that coat of plastic on it. That's a big no-no. Stick to the aluminum ones. So you do have to be aware when you're going out into the field not to contaminate the samples that you're going to be sampling. Tyvek is a big no-no. You don't want to use Tyvek in any way, shape, or form. There's certain gloves that you'll be wearing that PFAS was used in the manufacturing of those gloves. So you want to make sure your gloves are PFAS free. As far as the bottles are concerned, you want to stay away from anything Teflon, obviously, because PFAS was used in the manufacturing of Teflon. So it will leach out of the Teflon if you use Teflon lids. So the requirements right now are a high density polyethylene or a high density polypropylene plastic bottle. If you're analyzing for waters, there's a preservative called Trisma. It's a dechlorinating compound. You want to make sure that your samples are preserved with Trisma for waters. For soils, again, you want to use the same HPDE, high polypropylene, or high polyethylene. Sorry, I can't get that out. But you can use soils. Obviously, you got to follow the EPA guidelines of keeping them cool and shipped and all that kind of stuff. If you're doing tissues, you want to freeze the tissues. When it comes to rinse blanks and field blanks, you want to purchase either from a reputable manufacturer or from the laboratory PFAS-free certified water. Regular deionized water from a laboratory or regular deionized water from someplace that you would buy it in the local area, they will not cut it. It has to be certified PFAS-free water. And what you're trying to reduce is you contaminating your samples with PFAS, because we are looking at part per trillion levels. Hopefully I didn't scare you off in sampling, but that is some of the realities that we've talked about before.
Thanks, Ron. We had another question from Heather. She asks, can you briefly discuss the key differences between methods 537.1 and 533?
Anything else, Kelly, or can you guys not hear me?
I can hear you. Did you hear my question?
I did not.
Okay, it's Heather asked, can you briefly discuss the key differences between methods 537.1 and 533?
Yeah, that shouldn't be a problem. Did you say her name was Heather?
Yes.
Okay. Heather, if you can send me an email, I can get you a lot more detail on the differences in methods. 537.1, the big difference between 537.1 and 533 is isotope dilution. They're both solid phase extraction. They're both have a concentration. They both are for drinking waters only. And they have relatively similar compound lists. But the big difference is the isotope dilution. And I'm going to assume that, well, I'll just explain. So for isotope dilution, what the laboratory does, if you think about carbon, carbon has, the molecular weight of carbon is 12. It also has a carbon-13 isotope. It's a naturally occurring isotope. What the laboratory does is for the compounds that we're analyzing for, we will buy the carbon-13 isotopic equivalent of that compound. So if you're looking for PFOA, we will buy the carbon-13 PFOA as well. And we spike that into your sample at time or prior to extraction. And so we will extract out not only the PFOA, but the carbon-13 PFOA as well. And since the carbon-13 is going to act chemically exactly like the carbon-12, we're able to determine the percent recovery of the isotopic PFAS compounds and extrapolate that if we got 50% recovery of the carbon-13 compound, then that means we only got 50% recovery of the carbon-12 compound. So it enables us to get you a better understanding of the true concentration. So if we reported 5 parts per trillion, but only got 50% recovery of the carbon-13, then we're going to assume 50% recovery of the carbon-12. So that would jump your result to 10 parts per trillion. And that's the benefit of isotope dilution. And that is one of the reasons that the DoD came out and said in table B15 that you must do isotope dilution to be DoD certified. Other than that, there's not much difference. That 533 does a short chain, where 537 has longer chains, short chains, and some of the replacement compounds. And what I mean replacement compounds, the replacement for PFAS, Gen X, Adana, and such.
We have another question from Matt. He asks, what are your general thoughts on what methodology should be used for wastewater and or biosolids? And what are the pluses and minuses to using method 537.1 versus 8327 for these matrices?
Okay, the first plus and minus for the 537.1 versus the 8327. Okay, first of all, 537.1 is drinking water only. So we're going to be talking 537 modified. With 537 modified, there is a solid phase extraction using isotope dilution, and there's a concentration step. So the big three that you're going to have with 537 modified is you're going to have lower reporting limits, you're going to have more accurate results with the concentration or with the isotope dilution, where 8327 is a direct injection. Where the direct injection, you basically, it's a dilute and shoot. And you can see at the table that I have up there that the lower reporting limit for 537 modified and 537.1 and 533 is around 2, where the lower reporting limit for 8327 is 10. So with wastewaters and biosolids, I would go with more of the 537 modified, because the laboratories have modified those methodologies to handle wastewater. They have different solid phase extractors. You can get lower reporting limits, and they have the ability to extract out solid matrices. The sludge for the D7079 is really, if you think about it, more of a wastewater sludge, where they centrifuge it and they decant off the water and then analyze the wastewater.
We have another question from Teresa. Could you go over the QSM requirements for 537.1 modified for groundwater and soil?
Oh, man. How can I show my screen outside of the presentation?
We do
Can I
have
do
the
that?
screen sharing option,
Screen sharing? Okay.
but I'm not sure if, since you haven't done it before.
Yeah. There's several requirements, isotope dilution being one of them, meeting certain recovery limits for LCSs and matrix spikes and things like that, using a solid phase extraction. I would suggest, I mean, you can query, just go to Google, which is essentially what I was going to do there for a second, is just go to Google and type in QSM 5.1 table B15, and you'll see what the modifications. They're not modifications. They're basically saying you have to meet this criteria. You can modify the method any way you want, but this criteria have to be met.
And Teresa, if you wanted more information from Ron, you can feel free to send him an email as well. There was another question came in from Donald. He asks, the ITRC website has a table with regulation development, regulatory limits by state that is updated regularly. As an FYI, for instance, Florida has soil and groundwater provisional regulatory standards the state is utilizing to drive assessment and eventually remediation. I believe more states than the chart in the beginning of the presentation showed to have CTLs developed.
You're probably right. Like I said, these things change pretty quickly. This is basically, I didn't make this chart. I just kind of pulled the chart from Google, and it might be outdated. This is ITRC back in 2018. So you can see right there, it's 2018. I just wanted to bring this up for effect. But yeah, states are constantly bringing, more compounds online. More states are being certifications. These certifications are relatively new-ish. And each state is bringing certifications. So I can definitely see this information being outdated pretty darn quickly. And I'll make sure, and I appreciate you telling me this, I'll update this table accordingly.
And we had a follow-up question to Teresa when you were talking about the QSM requirements. She says that, she goes, I guess my question is more related to what additional samples would need to be collected in the field.
Yeah, that's a tough one for us in the laboratory. It really depends on their sampling plan. I do know that we have, we did here in Houston, we have refineries. If you guys remember, there were a couple of refinery fires a couple years ago. So with the waters, we did a lot of sample duplicates and a lot of rinse-ape blanks where we had PFAS free. We actually tested the foam because they use multiple foams out there. In Port Arthur, there was a fire not too long ago, again last year, where we did both methodologies. So it really is going to depend on your, similar to when you go out and do a typical sampling plan for non-PFAS, how many samples you're going to take, how many matrix spikes you're going to do, how many sample duplicates. Kind of follows along those same guidelines. You just come up with a sampling plan that would satisfy, the state regulators or the federal regulators that you're working with.
We had a question from Dwayne. He says, if these compounds are in so many products we use every day, how does the lab maintain cleanliness?
Well, first of all, the instruments that we buy, the LC triple quads, when we receive them, they are full of Teflon. They have Teflon tubings, they have Teflon washers, all that kind of stuff. And we literally have to have the manufacturer rip out all the Teflon and put high density polyethylene lines wherever there was using Teflon. The laboratories are separated from the most laboratories, we do BTEX, we do TPH, we do other things, and we also do PFAS. So the PFAS laboratory is its own entity. It does not share glassware with any of the other departments. It does not share personnel. It does not share, the air flow. We make sure that what we buy is PFAS free. We use PFAS free deionized water. And we actually have to buy it. We don't have in the regular lab, we have a DI water system where tap water comes in, goes through a series of filters and ion exchanges, and it comes out as deionized. Can't do that with PFAS. So there's a lot of techniques that the laboratory has to employ to stay in that cleanliness rate, especially since the reporting limits are so low and PFAS compounds are used in essentially everything. And like I said, when you guys are going out into the field, and down here in Houston, Texas, and Louisiana, during the summertime, you're going to want two things: sunscreen and bug repellent. Doesn't mean you can't use them. You just have to make sure they're PFAS free. And that's what we do here in the laboratory. Everything that gets utilized, we make sure is PFAS free. And when you guys send in a sample that is highly contaminated, it takes us a very long time to decontaminate our glassware and our instrumentation when that sample comes through and blows out the instrument. I see, go ahead.
No, go ahead.
No, I see the next question, so you can go ahead and read it.
From Meg, yeah, she asks, is there a PE program set up for laboratories for these methods?
Yes, there is. It's a relatively a new performance evaluation program, similar to what, PE samples, where we get unknown concentrations from regulatory agencies, and we have to run it and give them the right answers. That actually has become part of the certification process. So it's the PFAS methodologies are kind of falling in line with other methodologies that are out there, where we have to do performance evaluation samples for volatiles and semi-volatiles and so on and so forth.
It looks like Dave just had a comment. He said on August 3rd, 2020, Michigan adopted drinking water standards for 7 PFAS compounds. I believe these may be the most stringent in the country.
I would believe that. I think Michigan, I've done some work in Michigan, and Michigan is very proactive at this point. There's some states, and not to knock the state, but like Louisiana, they don't want to know about it. Texas kind of says, well, analyze for it. If you just sprayed foam all over the ground, we're going to analyze for it. But if it's not in your phase 1, then we won't analyze for it. Where Michigan really is like, yeah, you got BTEX, TPH, metals, PFAS. It's starting to get to that point in that state, just because of the contamination that they've had from it was a Wolverine, and of course the Air Force Base. It's in southern Michigan. So yes, they're getting very aggressive on the sampling and regulatory side of it.
And it looks like this might be our last question. It says, is there any toxicological research being carried out in the U.S. on the polyfluorinated compounds?
I don't know of anything specific like that I could point a finger to, but I do know that the federal government is doing toxicological research right now. And that's one of the arguments against PFAS or PFAS analysis, is the lack of toxicological studies out there. This stuff's everywhere. It's been everywhere since the 1950s and 60s, and everyone's not dropping dead, or we're not having the cancer everywhere. So do we really know this is toxic to us? Most of the toxicological effects have been determined by clusters. There's been huge contamination in this little town, and in this little town, we're seeing more of this. So there is research out there, or research ongoing, but toxicological, I'm not a toxicologist, but toxicological studies tend to take years. So it may be a few years until we absolutely get some hard facts on that.
Awesome. Well, thank you so much, Ron. I think that's the last of our questions we have today. Again, feel free to reach out to Ron Martino at alsglobal.com for any additional questions you may have. Again, thank you for everyone's time today, and for Ron for presenting this information. And we'll see you all next at our next webinar Wednesday series next week. Thanks so much.